Okay, so today we will talk about surface tension. First of all, you need to know which are cohesive forces and then which are adhesive forces. Okay, attractive forces between molecules of the same type are called cohesive forces. And then cohesive forces are responsible to hold the body of a liquid together with minimum surface area. Okay, and then you later find out that the cohesive forces are responsible for your surface tension. Okay, attractive forces between molecules of different types are called adhesive forces. Okay, so for the adhesive forces, right, these kind of forces are responsible to make the body of a liquid spread out. Okay, so that the adhesive forces will tend to maximize the surface area of the liquid. Okay, so now let's study about the cohesive forces between water molecules. And then when we mention water molecules, we know that they are polar molecules. And then we know there are hydrogen bonding between water molecules. Okay, so for example here H2O, 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 you have 4 water molecules all together here. And then you know that the oxygen atom is more electronegative than the hydrogen atom. So you know that electrons tend to spend more time around oxygen atom compared to hydrogen atom. Okay, so and then for the hydrogen atom, they have partial positive charge. And then when this is partial negative charge and then this is partial positive charge, you will have an attraction force. And then this attraction force is known as a hydrogen bond. Okay? So the cohesive forces are the forces between the same type molecules. Okay? Between water molecule and another water molecule. And then these cohesive forces are responsible for surface tension. So for water, hydrogen bonding is very strong. Okay, at least it is much stronger than van der Waals forces or some other intermolecular forces. Alright, so water has an irregularly high surface tension. In fact, other than mercury, water has the greatest surface tension of any other liquid. Okay, so let's take a look at this. This is a beaker, and then now you have some water in the beaker. Okay, so let's take a look at the surface tension of this water here. Okay, within a body of liquid, a molecule will not experience a net force because the attractive forces. Okay, what I mean by attractive forces are hydrogen bondings. Okay, by the neighboring molecules all cancel out. So you see this one. Okay, when the water molecules is within the liquid, right? Okay, the water molecule has hydrogen bondings with its neighbors in all directions. So you know that the net force on this water molecule is 0. At the water surface, okay, at this surface, molecules in the outermost layer have no neighboring molecules above. Okay, so above the surface of water, you only have air. You don't have any other water molecules anymore. Okay, so they have no neighboring molecules above, and thus exhibits stronger attractive forces upon their nearest neighbors on and below the water surface. Okay, so you know that for the water molecules on the surface, right, since they can only form less hydrogen bonding compared to the water molecules within the body of the liquid, then the hydrogen bonding here is much stronger than here. Okay, so net force on surface molecules is downward. Okay, so you see this, the left hand side and the right hand side, the forces actually cancel out, okay, horizontally. But then since there are no attractive forces from above, you only have attractive forces from below the surface, then the net force on each molecule on the surface is downward. Okay, so the surface particles are pulled down until counterbalanced by the compression resistance of liquid, and this causes the molecules on the surface to contract and to resist being stretched or broken. Okay, so once again I have to remind you that the hydrogen bonding here is much stronger than the hydrogen bonding here. Okay, so the water molecules at the surface actually form stronger hydrogen bonds, and then the surface molecules are actually a little bit closer together. Okay, so I should have drawn a lot of water molecules here, and then the water molecules are slightly further apart when they are within the liquid. Okay, so it's like a skin. This is a skin, this is a membrane. It's formed at the water surface. Okay, so now this is the water, and then you use your finger. Okay, you slightly touch the water surface and then you lift your finger. Okay, you can see that the water is slightly attracted by your finger, and then now you use your finger to poke the surface of the water. Then you can see that actually the water surface does not break. Okay, the water surface is still a continuous surface. Okay, it's still a perfect surface. It's just that it's like an elastic membrane, you know. Okay, so a surface molecule which is displaced by a tiny displacement is acted on by a restoring force due to the cohesive forces between water molecules at the surface. Okay, so you know that the hydrogen, let's say there's a water molecule here, and then there's a water molecule here. The water molecule here will attract this water molecule, and then the water molecule here will attract this water molecule. Okay, so that the cohesive forces between the water molecules on the surface will actually help to make sure the surface of the water is not broken. Okay, so surface tension could be defined as the property of the surface of a liquid that allows it to resist an external force. It is more difficult to move an object through the water's surface than to move it when it is completely submerged, or you can say that it is completely submerged. Okay, so now let's consider a liquid drop. Okay, a liquid droplet. Okay, so yeah, this is water molecules, and then this is the liquid drop. So within the droplet, a molecule will not experience a net force because the attractive forces by the neighboring molecules all cancel out. Okay, so you know that the hydrogen bondings are in all directions. Okay, at the water surface, okay, on the surface, the outermost layer of molecules has no neighboring molecules outside the droplet, and thus exhibits stronger attractive forces upon their nearest neighbors on and below the droplet surface. So for these molecules at the boundary, there will be a net inward force causing the molecules on the surface to contract and to resist being stretched or broken, and this also explains the characteristic spherical shape that the droplet forms. Okay, so you see, like I said, the hydrogen bonding on the water surface is always the strongest one compared to the hydrogen bonding within the droplet. Okay, so yeah, you know that you don't have any attractive forces above or outside the droplet, so the net force on the water molecules on the surface is actually inward. Okay, and then the net force on the molecules within the droplet is zero because they actually cancel out. Okay, so in fact, because the hydrogen bonding at the surface is the strongest, I should have drawn that the surface molecules to be a little bit closer together like this. Okay, so they are supposed to be very close to one another at the surface. Okay, so surface tension is measured as the energy required to increase the surface area of a liquid by a unit of area. The interior molecules have as many neighbors as they can possibly have, so they are quite stable and therefore they are in a lower energy state. Okay, so you see this, when the interior molecules can form hydrogen bondings with their neighboring molecules, as many as possible, then you say that the interior molecules are more stable, therefore they have a lower energy state. Okay, So the boundary molecules have less neighbors, so they are less stable and therefore they are in a higher energy state. Okay, so you know that because the water molecules are on the surface, they cannot form as many hydrogen bondings as they want, so they are less stable, so they have a higher energy state. Okay, so the same goes here. Okay, the surface molecules cannot form as many hydrogen bondings as they want, so they are less stable, so they have a higher energy state. And then the interior molecules have a lower energy state because they are more stable, because they can form a lot of hydrogen bondings with their neighbors. Okay, so for the liquid to minimize its energy state, the number of energetic molecules on the surface must be minimized, thereby resulting in a minimal surface area. Okay, so you know that the cohesive forces which are responsible for surface tension, they will make sure that the liquid have a minimal surface area because they actually want the liquid to be in the lowest possible energy. But then the adhesive forces do the opposite. Okay, so surface tension is the tendency of liquid surfaces to shrink into the minimum surface area possible. Okay, so let's now take a look at the contact angle. Contact angle is the angle between the tangent to the liquid surface and the object surface. Okay, so for example, you have 3 liquid droplets here. Okay, this liquid droplet tends to spread out, and then for this water droplet, it tends to retain a beautiful spherical shape. And then this is the contact angle. Okay, the contact angle is the angle between the object surface and then the tangent of the water surface. Okay, so for example, if you see this droplet light, it tends to spread out, so you know that the surface tension effect is less obvious. Okay, because like I said, the surface tension effect will make sure that the surface area of the droplet to be minimized. But then since this is spread out, it has the maximum surface area, okay, compared to these two. Okay, so the contact angle is actually an acute angle. Okay, the contact angle is between 0 degree and 90 degree. Okay, so you say that the adhesive forces between the water molecules and the surface molecules are greater than the cohesive forces between the water molecules in the droplet. Okay, so for example, this is like a water droplet on polar surface like glass. Okay, for your information, glass molecules actually they are more polar than water molecules. Okay, so let's take a look at this one. For this droplet, the surface tension effect is really obvious. Okay, because the surface tension effect will make sure that the overall surface area of the liquid is minimized. Okay, so that the whole liquid can stay in the lowest possible energy state. Okay, so the cohesive forces is greater than adhesive forces. Okay, so example, the water droplet is on non-polar surface like waxed surface. Okay, so yeah, do you still remember that this is an acute angle, and then this is a right angle, and then this is an obtuse angle? Okay, so you realize that the greater the effect of surface tension, the greater the contact angle will be. Okay, and then of course the contact angle will not be larger than 180 degrees. Okay, so first of all, let's take a look at this equation. Surface tension force is equal to gamma times the effective length. Okay, the gamma, right, is the surface tension coefficient. Effective length is the length where surface tension forces add on. Okay, so this is the unit of this is Newton. This is Newton per meter. This is meter. Okay, and then you know that actually surface tension force is a very, very, very tiny force. So you actually need a smaller unit. Okay, so 1 dyne of force is 1 times 10 power negative 5 Newton. Okay, a ring of radius r, okay, the radius is r, and mass m is kept at rest on surface of a liquid of surface tension coefficient gamma. Find the force required to lift the ring above the liquid. So now you are going to take the ring out of the water, okay? So you want the ring to be out of contact with the water surface, and while you are lifting, you can see that actually the surface tension will act downwards. Okay, so the force required to lift the ring is equal to the weight of the ring plus the surface tension force in downward directions. Okay, so you have to resolve the force in the vertical direction. Okay, and then F equal to mg plus gamma is the coefficient times your effective length. Okay, the effective length is this circumference, this inner circumference, and also the outer circumference. So you have 2 times 2 pi r cos theta. Of course, we assume the ring is very thin. We assume that the circumference here is exactly the same as the circumference here. Okay, so the salt film exerts a force on the sliding wire, this is sliding wire AB, in an attempt to reduce its surface area, and the magnitude of this force depends on the surface tension of the liquid. Given that the coefficient of surface tension is gamma, find the magnitude of an external force F such that the sliding wire can be fixed in place. So if you want the sliding wire to be fixed, then you have to make sure that the force that you apply is exactly the same as the surface tension force. Okay, so okay, the effective length here is 2L. Okay, because remember that this is the surface of the salt film. You have your upper surface and then you have your lower surface. Okay, so for the upper surface we have one length here. For the lower surface, we have another length here. Okay, so the effective length is actually 2L. So the surface tension force is actually gamma times 2L. Okay. So now we want to put a needle on the water. Okay. Given that the length of the needle is 0.05 meter and then the gamma is 72.8 dynes per centimeter, please find the maximum mass of needle if you want to put it on the water, to put it afloat. Okay, so for example, when the mass of the needle is less than the maximum value of the mass possible, you will realize that the surface tension force is in this way, is in this direction. Okay, because okay, you know that the surface tension force will act tangential to the area of the needle here, to the area of the water surface being curved here. Okay, and then when the mass of the needle is maximum, in a way that you want to make sure that it stays afloat. Okay, so if m is greater than maximum max, then you know that the needle will sink into the water. Okay, so when you know that the mass is maximum, the contact angle is actually 0, because you know that when theta equal to 0, cos theta equal to 1, which is the maximum value of cos function. Okay, so the surface tension force will act directly upwards. Okay, so the surface tension force is equal to gamma times the effective length cos theta equal to mg. When m equal to m max, cos theta equal to 1 because theta equal to 0, because the surface tension acts directly outward and then the contact angle is 0. Okay, so you substitute everything, and then you have to remember that, let's say this is your water surface, this is your needle. Alright, then the effective length is this length and also this length. Okay, of course we assume the length here and here is very negligible. Okay, so the effective length is 2L. Okay, 2L. Okay, and then you can know the maximum mass of needle. So if m equal to 0.5 gram, then what is the contact angle? Okay, then you use the same formula to find yourself. Okay, so now you want to put a paper clip on water surface. Okay, now this is a paper clip, and then you know that you want to make sure the paper clip to be afloat on water surface. So once again, you use the same formula. And then you have to remember that when m is maximum, the theta equal to 0, the contact angle is 0, and then the cosine function has the maximum value possible, okay? And then, may I know the effective length, which is the length where the surface tension forces will act on, okay? The length is here, here and 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 here, okay? So you know that the effective angle, the effective length is 2 times the total length of the clip, okay? So now you have a water bug, okay? This is an insect, or maybe we call it a water strider, okay? So this is a water strider, and then a 3 times 10 power negative 5 kilogram water bug with 6 legs, okay, with radius 0.2 millimeter for each leg, is walking on the water. Please find the contact angle of each leg with the water. So once again, you use the exactly same formula, but then you have to know that what is your effective length. Your effective length is 6 times 2 pi r, okay? Because for each leg, the effective length is here, the circumference of your leg. And then now you have 6 legs altogether, okay? So yeah, you find the theta. So you have to remember that the water striders can actually float on the water surface because of the tension force, and then the surface tension is actually due to the strength of cohesive forces between the water molecules, and then the cohesive forces between the molecules are what? Are the hydrogen bondings, okay? Are the attractive forces between the water molecules. In a cylindrical vessel, at its bottom, a round hole of diameter 1 millimeter is drilled, okay? So you drill a hole, okay? And then some water is poured into the vessel, okay? You pour some water. Find the maximum height to which the water can be filled in it without leakage, okay? Without the water leaking out of this tiny hole here. Take surface tension of water to be 75 times 10 power negative 3 Newton per meter. Density of water is 1000 kilogram per meter cube, and then gravitational acceleration is 10 meter per second, and then the angle of contact is 0. Okay, so you say that the liquid will start leaking out when the pressure force is greater or equal to the surface tension force, okay? The surface tension force, right? FST equal to gamma L effective. Gamma L effective. L effective is what? Is the circumference of the tiny hole here, okay? So you know that the radius is the radius of the tiny hole here, not the radius of the whole cylinder here, okay? Okay, so the pressure force is what? The pressure times the area, okay? The pressure at the bottom of the vessel. Okay, so you know that the pressure of water at the bottom of the vessel is rho gh, and then the area of the tiny hole is pi r squared, okay? Then you can find the maximum height, okay? So once the height of the water reaches 0.03 meter, then you know that some water will start leaking out. A film of water is formed between two straight parallel wires, each 10 cm long, at a separation of 0.5 cm. Please calculate the work required to increase the separation by 1 mm, given the surface tension of water is 72 times 10 power negative 3 Newton per meter. Okay, so you know that the definition of the surface tension is what? Is the energy required to increase the surface area of a liquid by a unit area, okay? The surface tension is measured as the energy required to increase the surface area of a liquid by a unit of area. So you know that dE equal to gamma dA. dE equal to gamma dA. So you know that gamma equal to dE over dA, which is the energy per unit area. Okay? Okay, so yeah, the work done is equal to the increase in the energy which is used to increase the surface area of the water-air interface by a certain area. So dE equal to gamma dA. And then what is dA, please? The dA is the increase in the surface area of the interface of water and air. Okay? L times delta X is for upper layer only. So the water has upper surface and lower surface. So you need to multiply it by 2. Okay, so this is how you know that the energy of 1.44 times 10 power negative 5 joule is required to increase this surface area. Okay, and then these surface areas include the surface area of the upper and the lower layer. Okay, the upper and the lower surface. Okay, last but not least, let's try to see the purpose of we using detergent or shampoo or soap in order for us to clean things. Okay, so the key part here is that when you use detergent or shampoo or soap or whatever, you know that the surface tension of the water is decreased. Okay, so that they can clean things more successfully. Okay, and then you have to remember that when we take a look at the molecules of the detergent or the shampoo or soap, we know that one end of the chain is hydrophilic. And then what do you mean by hydrophilic is that the end will be attracted to water because this end is a polar end. Okay, so for example, you take a look at this one. The oxygen atom here has a partial negative charge. Okay, has a negative charge here. So you know that this is polar. Okay, so it can attract polar molecules like water molecules. And then another end is hydrophobic. Okay, which means this will repel water molecules, and then this can attach itself successfully to some other oil molecules. Okay, and then this end can attach easily to grease. So in a soap and water solution, the hydrophobic ends of soap molecules do not want to be in the liquid. So they will try to find their way to the surface of the solution, squeezing their way between the surface water molecules in order to push the hydrophobic ends out of water. And this separates the water molecules from each other on the surface of the solution. So as the distance between water molecules on the solution surface increases, the surface tension forces become smaller. Hence, the attractive force, the hydrogen bonding between water molecules on the surface becomes smaller. So like I said just now, when you take a look at the water droplet or maybe the water, okay, you know that the water molecules on the surface, they will be closer to one another because you know that the hydrogen bonding between the water molecules on the surface is the greatest compared to the hydrogen bonding within the liquid. Okay, so if the soap molecules are able to squeeze themselves in between the surface molecule, so that means that, okay, this is your soap molecule. Okay, the soap molecule will be here, 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 will be here. Okay, so you know that the distance between the surface molecules, the water molecules on the surface increase. Okay, and then since the distance between the water molecules on the surface increases, therefore you will have some weaker hydrogen bonding on the surface, so you have less cohesive forces on the surface, so you have less surface tension, so that you can clean your things easily. Okay, so in the next video we are going to talk about the pressure difference across a curved surface. Thank you.